to Mengtao Tang. So Mengtao, can you share your screen? And start when you're ready. You will tell us about the REST UV spectroscopy of reionization analogs at redshift 1 to 3 and implications for early star-forming galaxies.
Okay, so thanks for the organizer to give me this opportunity to talk. My name is Mengtao Tang from University of Arizona. So today I'm going to talk about our new results from the rest frame UV spectra of reionization-era analogs at redshift 1 to 3. So in the last few years, we have obtained our first view of the spectral properties of galaxies in the reionization era. So we learned from the SAZERAC data is that the optical line emission in galaxies at redshift larger than 6 is incredibly intense. Upward to 20% of this population has O3 plus H beta equivalent with larger than 1,000 angstrom. So this means these galaxies are in the midst of the burst of star formation. So this kind of extreme emission-like galaxies is very rare at redshift 2, but seems pretty common at redshift 7. So what do we know about their physical nature? So currently, we learned two things from their spectra, which seems quite surprising. So the first one, as we heard from the last talk given by Ramesh, is that the carbon-3 emission in these extreme bursts of galaxies in redshift larger than 6 are often detected with the equivalent width about 20 angstrom. So this value is much, much larger than the typical value at a lower redshift. So currently, we can hardly find such strong carbon-3 emission at a lower redshift, which makes it very difficult for us to interpret the what this line emission tells us about this extreme population. So the second result is from the Lyman-alpha emission in the galaxies in the reionization era. So we know that the Lyman-alpha emission is very rare in the general population of redshift 7 to 8, as you can see from this plot showing the Lyman-alpha fraction. This is expected as the AGM is scattering the Lyman-alpha. However, if we look at the subset of population of massive galaxies with very large O3 plus H beta equivalent width, we see that the strong Lyman-alpha emission is quite common in this population. So why this Lyman-alpha is so strong in this population at redshift 7 is still unclear. There are two possible explanations for this. So first is that this kind of massive galaxies may sit in the larger ionized bubbles that with the accelerated reionization. And the second explanation is that these kind of extreme optical line emitting galaxies have more intense radiation field than the general population at redshift 7, which boosts both the production and the escape of the Lyman-alpha photons. But without a better understanding of the galaxies with extremely large O3 plus H beta equivalent width, it's hard for us to answer these questions. So one way to address this uncertainty is at a very high redshift is to take a spectra of galaxies with similarly large optical line equivalent width at redshift 1 to 3, where we can study them in greater detail. So motivated by this, we selected galaxies with very large O3 plus H beta equivalent width from a few hundred to 1,000 angstrom at redshift 1 to 3, which the values are comparable to what we're seeing at a redshift larger than 6. So previously, we have a large near-infrared spectroscopy survey targeting the rest frame optical emission line for this population. So this is the second step of our survey. We use the optical instrument to target the rest frame UV lines for this population. So we obtained the rest UV spectra for 100 galaxies at redshift 1 to 3 with large optical line equivalent width, including 68 of them with O3 plus H beta equivalent width larger than 1,000 angstrom. So our goal is to explore the carbon-3 and the Lyman-alpha property in this population, and we will use our analogs as a baseline to understanding the results we see in the redshift larger than 6 and 7. So first, I show the carbon-3 emission results. From the last talk given by Ramesh, we heard that the carbon-3 emission reaches about 20 angstrom in the galaxies with very large O3 plus H beta equivalent with about 2,000 angstrom. So if it's the case, it indicates that the gases with strong carbon-3 emission is just due to the hard radiation field from very young stellar populations. So if it's the case, do we see the same intense carbon-3 emission in our galaxies with very large optical line emitters? So here I show, I test this scenario with our sample. Here I show an example with very large O3 plus H beta equal with about 2800 angstrom. So if the carbon-3 is uniformly strong in this population, we fully expect to see a carbon-3 equal with about 20 angstrom in this object. But surprisingly, when we measure the spectra, we found the carbon-3 equal with only 8.5 angstrom for this object, much below what we expected. So what's happening here? Here I'm showing another example with O3 plus H beta equal with about 1700 angstrom. And also, we found the carbon-3 equal with is about only 7 angstrom. So from these two examples, we see that there's a very different population from what we heard from Ramesh, that not all the galaxies with extremely large O3 plus H beta equal with have strong carbon-3 emission. This means that the hard radiation field associated with the young stellar population is not sufficient to power the carbon-3 emission, strong power emission. So why do some of these strong O3 line emitter show relatively weak carbon-3 emission? So we investigate this with our full ionization models, and we found that the answer is metallicity. Metallicity also plays a very important role in regulating the carbon-3 emission. Here I show two examples with both large O3 plus H beta equal with, but one is a weaker carbon-3 emitter, and another is a stronger carbon-3 emitter. For the weaker carbon-3 emitter, it is more luminous and with moderately metal poor gas with about 0.3 solar metallicity. For the strong carbon-3 emitter, it's much fainter and with more metal poor gas, about only 0.1 solar metallicity. So we see here that the carbon-3 equal with increases by 3 times between 0.3 solar metallicity to 0.1 solar metallicity. Even they have even they have very similarly large optical line equal width. So what this implies for the galaxies in the Reionization-Era is that the strong carbon-3 emission found in redshift larger than 7 is also found in massive galaxies. Our results show that such strong carbon-3 emission also requires a very low metallicity, say 0.1 solar metallicity in these massive galaxies. So this indicates that this strong carbon-3 emission can be explained by the galaxy population shifted toward both a larger specific star formation rate, which is a larger O3 plus H beta equal with, as we heard from Ramesh, and also the lower metallicities, say 0.1 solar metallicity. So in the last few minutes of my talk, I'm going to talk about the Lyman-alpha result from the Reionization analogs in my sample. So recall that the goal is to explore the Lyman-alpha properties in the population with a very large O3 plus H beta equal with to provide a baseline to understand why Lyman-alpha is very strong in this population in the Reionization-Era. So here I show an example of our galaxies with a very large O3 plus H beta equal with, say, 2400 angstrom. And we also see a very large Lyman-alpha equal with over 100 angstrom. So this will provide a baseline to understand how the Lyman-alpha emitter fraction vary with the O3 plus H beta equal with. So here's our results. We see that for galaxies with very large O3 plus H beta equal with, the strong Lyman-alpha emission line is more common in this population at redshift 2 to 3, where the IgM is mostly ionized. So this suggests that the strong Lyman-alpha emission seen in this population at redshift 7 may not only be a result as the sitting in the large ionized bubbles, which can boost the transmission of the Lyman-alpha through the IgM. So what drives this trend in the redshift 2 to 3? So this can be explained by looking at the radiation field in this population. So here I show how the ionizing photon collection efficiency versus O3 equivalent width. With the galaxies with very large O3 equivalent width, they are also they are also the most efficient sources producing ionizing photons. So this also means that they are producing more ionizing photons and likely the Lyman-alpha photons than galaxies with the lower equivalent width. So galaxies with a very large O3 plus H beta equivalent width are likely to be more easily detected with Lyman-alpha. So what this implies for in the reionization-era is that the galaxies with the O3 plus H beta equivalent width and hence the radiation field plays a very important role in regulating the Lyman-alpha equivalent width. So when we compare the Lyman-alpha fractions in galaxies over the cosmic time, especially to the reionization-era, we must control these parameters, such as the intense radiation field. So for more information about the IgM surrounding this population in the reionization-era and about the IgM attenuation for these galaxies, you can see more in Ryan Ansley's poster presentation. So here I summarize my talk. We lead a large array frame UV spectroscopy survey targeting galaxies with very large O3 plus H beta equivalent width at redshift 1 to 3, which can be used as an analog of reionization-era galaxies. We're targeting their carbon-3 and Lyman-alpha emission. We found that the Lyman-alpha, the carbon-3 equivalent width, there's a large variation even in galaxies with very large O3 plus H beta equivalent width. This suggesting that the large specific star formation rate is not sufficient to power the intense carbon-3 emission. The carbon-3 emission, about 20 angstrom, also requires a very metal-poor gas, reflecting a shift of the redshift larger than 6 galaxies toward both a large specific star formation rate and a lower metallicity. We found for galaxies with very large optical line equivalent width, the strong Lyman-alpha emission become more common, and this can be explained by a larger Lyman continuum and also a Lyman-alpha production rate in this population. So the oxygen-3 equivalent width and hence the radiation field plays a very important role in regulating the Lyman-alpha equivalent width. So these factors must be controlled when comparing the Lyman-alpha fraction over the cosmic time. So I will stop here and take any questions.
Thank you, Mengtao. We have quite a few questions, so we'll try to get through as many as we can. So Daniel Scherer asks, have you been able to measure directly the metallicity over each of your C3 emitters to confirm the low metallicities you're suggesting?
There are very few objects with the O3 1660 measurement, so we can measure the metallicity for a bunch of sources. The number is small, but they are consistent with what we inferred from the polarization model and also the metallicity variation in carbon-3 emission.
Okay, so Yurit asks, nice results on the dependence of Lyman-alpha fraction on the O3 plus H beta equivalent width. How do the Lyman-alpha equivalent width you measure in the extreme emitters, O3 plus H beta emitters at redshift 2 compared to the Lyman-alpha equivalent widths measured at redshift 7 objects with comparable O3 plus H beta? Did you consider using the difference to infer the relative IgM attenuation? So I guess it's asking about.
Actually, another interesting result I haven't shown in this presentation is that we found the Lyman-alpha fraction in the galaxies with large optical line equivalent width are similar for both at redshift 2 to 3 and redshift larger than 7. Both of them show about 50% show strong Lyman-alpha emission with equivalent larger than 25 angstrom. So this may indicate that the first thing is that the Lyman-alpha production is larger in these galaxies with very large optical line equivalent width. And also the similar Lyman-alpha fraction we found at lower redshift and in the reionization-era may indicate that these galaxies also require a large, trace a large ionized bubble, which boosts the transmission of Lyman-alpha through the neutral IgM, through the IgM.
Okay, yeah. So probably have time for one more, although there are quite a few more. You'll have to go into the chat and answer there. But Charlotte Mason asks, beyond the Lyman-alpha emitter fraction, have you looked at the Lyman-alpha equivalent with distribution for these strong O3 emitters?
I have, let me see. I haven't looked at the Lyman-alpha equivalent with distribution for the O3 line emitters, but I think the distribution should be very similar to what we see. Should be similar to what we see in the redshift 7, as they show a similar fraction of strong Lyman-alpha emission. So for the Lyman-alpha equivalent distribution redshift 7, you can see the poster presentation from Ryan Ansley.
Great. That's unfortunately all we have time for. There's a few more questions, but we have to move on. So thank you again.